Good morning, good afternoon, good evening, or good night, depending on when you are viewing this. Today we're looking into the concept of z-scores. This is a tool that helps us measure and compare data in a way that works across different sets of information. Now let's walk through each point. Identify and describe the location of every score in a distribution. In social science, you might survey a group of people on a certain topic, like how strongly they support a certain policy, on a scale of 1 to 5. A z-score tells you whether someone's response is higher or lower than the group's average, and by how much. Think of a study where participants rate their level of stress. A z-score helps you see if the person reported stress is typical, or whether they're reporting much more or much less stress than everybody else. Standardize an entire distribution. Standardizing means taking all the responses and converting them so that they can compare on the same footing. For example, if one group of people answers a 10-point scale about their satisfaction with public transportation, and another group answers a 7-point scale, we can convert each group's response into z-scores. That way we can figure out who is truly more or less satisfied despite the different scales. Take different distributions and make them equivalent and comparable. Z-scores are like a translation system. In social science, you might compare data from two different communities or countries where people have been asked to rate their trust in the government. Even if one study used different methods or scales, Z-scores allows you to make meaningful comparisons about trust levels. It's also useful if you collect data about similar social attitudes at different times. So maybe you did a 2010 survey using a 5-point Likert scale, but in 2020, you used an 8-point scale instead. Converting them both into z-scores gives you a fair way to see if attitudes have shifted over the decades. Z-scores are also called standard scores. We will see both terms used to mean the same thing. Converting scores into a shared measurement that tells you how far above or how far below the response is. This helps social scientists figure out patterns, such as whether one group's viewpoints are off the charts high or low compared to another group, even if they were originally measured in different ways. With z-scores, we're basically leveling the playing field for data. No matter where or how it's collected, that's a big advantage for anyone working in fields like psychology, sociology, and political science. Take a look at these two different distributions of exam scores, each with the same average or mean of 20. However, they differ in something called their standard deviation. One has a small standard deviation of 2, and the other one has a larger standard deviation of 10. So let's break down what that means. Same mean, different spread. Both distributions center around 20. In the top figure, most exam scores cluster tightly near 20, creating a narrow peak. That's because the standard deviation is only 2. The bottom figure, the scores are much more spread out. Some are quite low and some are fairly high, and fewer are in the middle. That indicated by a larger standard deviation of 10. So why standard deviation matters? Standard deviation tells us how spread out the data is. When it's small, like 2, most scores land near the mean. When it's larger, like 10, there's a wider range of scores. If you think about social science research, this can happen in opinion surveys too. Maybe you surveyed how strongly people support a new policy and the average rating comes out the same in two different communities. A smaller standard deviation means that the most people in one community have similar views. They mostly agree or mostly disagree. While a larger standard deviation means there's a bigger range of opinions in the other community, some very supportive, some strongly opposed. Interpretation in real life terms. So in a classroom, a small spread, like the top figure, means that the student scores are pretty consistent. Maybe everybody studied the same material and ended up with really similar results. A large spread, like the bottom figure, might mean that you had some students scoring very high while others scored really low, with a few people in the middle. This could be because they had different levels of preparation or different approaches to the material. The main point that standard deviation doesn't change the average score itself. Both classes can look the same by mean alone, but the standard deviation tells you whether those scores or opinions or responses are tightly grouped or scattered apart. Z-score location and distribution. So on this slide, we're talking about z-scores, which tells us whether a particular value sits within the group of numbers, also called a distribution. There are two parts to a z-score. The sign, plus or minus. A positive sign means that the score is above the average mean. A negative sign means the score is below the average. So remember, plus above the average, negative below the average. The number. This part tells us how many standard deviations away from the mean the score is. So a z-score of +2 So if we have a z-score of +2, that means that the score is 2 standard deviations above the mean. So if the mean is here, then it would be 2 standard deviations above the mean. Whereas 1.0 means it would only be 1 standard deviation. And if it was a -1, then it would be below. So why does this matter? In social science, you might survey people on their satisfaction with community services, where the average rating turns out to be, say, 6 out of 7. If one person's z-score is +1.5, we immediately know that they are above the average satisfaction level, specifically 1.5 standard deviation above it. That helps researchers know and see how this individual differs from the typical respondent. These z-scores let us compare individuals or groups across various studies. So if we were to have a set of scores on attitudes towards environmental policies and another set of scores on attitude towards health policies, different scales, you could convert both of them into z-scores. Then you could see who is more enthusiastic or more skeptical across those different topics, even though those original scales were not the same. So that's the power of z-scores. They pinpoint whether that score is above or below the average and how far away from the average it really is. On this slide, we're looking at a normal distribution curve with the mean in the middle. The horizontal axis shows z-score values. So when we look at the center of the curve, z = 0. This point is the average or mean. A z-score of 0 means that the score is right at the mean. In social science surveys, a respondent at z = 0 would have a viewpoint that is exactly in line with the overall average. So this right here, if it would work, would be the overall average. Now moving left to the negative score. So as we move to the left, for example, we'll go z equals -1 or z equals -2. That score is below the mean. So that would be a -1, and then that would be a -2. The further left, the more unusual or rarer that score becomes. So if we're looking at a study that measures people's trust in the government, a person at a -2 would be much less trusting than most of the group, since that's 2 standard deviations below the mean. When we're moving right, so z equals +1 or z equals +2, the further the right, the more unusual these higher scores become. So if you're researching neighborhood satisfaction, someone with a +2 would be far more satisfied than the typical community member, since they're 2 standard deviations above the mean. So again, the numbers -1, -2, +1, +2, etc. tells us how many standard deviations away from a score that it lies from the center. Whether you're setting attitudes, exam scores, or numerical data, z-scores help you see if a person or a group is close to average or stands out. So this is the z-score formula for a population. Let's break this down, okay? X is the raw score. This is the actual value someone gets. In social science, it might be a survey response or a test score. If someone rated their trust in the government on a scale of 1 to 8 and they picked 8, that would be their X, okay? Now, this is our population mean. And this is the average score across the entire group or population we're studying. Suppose the average trust rating was 5. Okay. Now we have the population standard deviation. Okay, this number tells us how spread out the people's scores are. Maybe the standard deviation for trust is 1.5. Now we would put it all together. So the numerator right here, okay, we have the raw score minus the population mean. So that would be 8 minus 5. So that would be 3. And then we would divide it by 1.5. And that would equal 2. So the z-score would be +2. So that means that this person's rating was 2 + 2, so 2 standard deviations above the group's average. This is why z-scores are so handy. No matter what the score or topic you're studying, it lets you pinpoint the person's score and where it stands next to the relative average. So on this slide, we see the relationship between a z-score and a raw score. So we start with this formula, which we had on the other one, and we can solve for x to get this. So rearranging the formula. So basically, we're undoing what we did to get the z-score. Instead of subtracting the mean and dividing the standard deviation, we add back the mean and multiply that by the standard deviation. So if we know how many standard deviations above or below the mean you are, so your z-score, you can find out the actual score for x. So that would be the original scale. Think of it like mapping a place on a standard map back to your local neighborhood. The z-score is your coordinate in the standardized world, and your formula tells you the real address. So let's say you had a mean trust rating of 5, okay? And then your standard deviation, like we had before, is 1.5, okay? And you had your z-score of 2.0, okay? Then you would obviously, it would be 5 plus 3.0, and that would equal 8. So your x equals 8. This means that the +2 in the survey translates to the raw trust score of 8. So someone with a trust score rating of 8 is 2 standard deviations above the community average. It's a simple way to switch back and forth between a standardized number, z-score, and the raw data, x. If you have any questions about how this works, just remember that z-scores and raw scores are 2 ways of looking at the same information. One is standardized and the other one is in the original form. By now, you've seen that z-scores are often discussed for entire populations, where we have the population mean and the population standard deviation. But it is also possible to calculate z-scores on smaller samples within that population. So, in a perfect world, we have data from everyone in a population, and we would use the population mean. And the population standard deviation. I apologize for how bad these look. But in social science research, we don't always have the data for the entire population. Instead, we often study a smaller group called a sample, which you should know by now. So when we look at z-scores in a sample, when we use that sample data, we replace our population with our sample mean. And with our sample standard deviation. Oh, that's a lowercase. This is lowercase. The idea remains the same. A z-score tells us how far a particular score is from the sample mean, measured in units of that sample that standard deviation. You know, you would think my brain would work better. Not today. This indicates the relative position of the score in a sample. whether it's above or below the sample mean, and how many of our sample standard deviation it is. So it's the same principle, it's just different symbols. Once we transform the entire sample distribution into z-scores, it has the same shape as the original data, but a new mean and a new standard deviation. The differences is that we are using our M and our S instead of our population and population mean and our population standard. Oops. You know, my computer doesn't want to work today. So imagine we're studying communities' involvement in different districts and we only survey 50 residents. So that is our sample. We find the average number of local meetings attended, which is 2, with a sample standard deviation of 1.5. If the particular individual reports attending 5 meetings, we can calculate the z-score using the M and the S. This helps us see whether the person is a typical participant or an outlier. Even though we don't have the entire population data, the z-score still helps us pinpoint where that person stands to that sample. So now we are going to do, if my thing would work, no, of course not. We're going to do a learning check. A z-score of +1 indicates a position in the distribution is either it's above the mean by 1 point, above the mean by a distinct equal to 1 standard deviation, below the mean by 1 point, or below the mean by a distance equal to 1 standard deviation. Obviously I messed up and I showed you anyways, which is above the mean by a distance equal to 1 standard deviation. I know that a lot of people would automatically jump to above the mean by 1 point, but it's not a point. It is 1 standard deviation. Now, describe if each of the following statements is true or false. A negative z-score always indicates a location below the mean. This should be very easy. This should be very easy. True. Negative will always be below. A score close to the mean has a z-score close to 1. Let's see. Let's see if you guys are right. Okay. The first one is, of course, true. The sign indicates the score is below the mean, but this is false. Scores quite close to the mean of the z-scores, it can be either plus or minus, right? Because it can go above or below. Oh my goodness, that looks like a face. You guys are like, what is happening right now? Sorry. Okay. So we have to look at how z-scores connect to 4 key pieces of information. So first we have the raw score, which is going to be x. Then we have the mean. Again, I apologize for how bad this looks. Then we have the standard deviation. We have the z-score. Because these pieces are tied together by a formula, we know that if we have any 3 of them, you can solve for the 4th. Okay, so because we have all the pieces, they're tied together with our formula or our z-score. If we know any 3 of them, you can solve for the 4th. So if we're trying to find the standard deviation, if someone tells you that the mean is 50 and the raw score is 60 and their z-score is +2, we can just plug that in and we can solve for our standard deviation. So what we would do, so 2 equals 60 minus 50, which would be transferred over to, and you can't see over here, so we'll put it right here. So that would equal 5. Okay, so if we wanted to find the mean, then we are going to do, let's erase. Boop. Oh my goodness, this just doesn't want to work for me. Okay, we're going to erase all the ink on the side. Okay, so let's find the mean. So again, so we have the standard deviation. So then this is going to transfer over. So we're going to, now this looks like an N, but it's not. To 60 minus 2 times 5, and that would equal 50. So you can think of it like a puzzle. With any 3 pieces in place, we can figure out that missing piece. So this shows you a normal bell curved shape distribution, illustrating how 2 specific values, 59 and 65, relate to the mean and standard deviation. Notice that 59 is on the left side of the curve and 65 is on the right side. And there is a 6-point gap in between. So most likely what we're looking at here is test scores or survey results. And the question they're probably asking is what proportion or probability of the distribution falls between these 2 numbers. The figure indicates that these 2 points, 59 and 65, are each 1 standard deviation away from the mean, but in opposite directions. This means the mean is right in the center of 59 and 65. So it's presumably 62. Since 62 is 3 points above 59 and 3 points below 65. The standard deviation would be 3 because each point is 3 units from the mean. So going from 59, 1 standard deviation below the mean, to 63, 1 standard deviation above the mean, covers a particular portion of this normal curve. So a normal distribution, about 68% of all the values lie within 1 standard deviation of the mean. So if we're dealing with test scores, roughly 68% of people in your sample should have scored between 59 and 65. So we're also again looking at a normal bell-shaped curve with z-scores marked at the -2, -1, 0, +1, and +2. Directly underneath those z-scores, you see corresponding raw scores on the x-axis. So you have 42, so this at the -1, you have 54 at the +2, which means that our mean is in the middle. So here's what to notice. The figure shows that from 42 to 54, there's a total of 12 points, which covers the span from -1 to 2 on the z-scale. So this should be about 3 points, 3 standard deviations. By looking at the axis, the mean must be right in the middle of 42 and 54. So let's do a learning check. For a population with 50, the population mean is 50, the standard deviation is 10, and the z-score is 0.04. Which raw score does it correspond to? Okay, so we're looking for x. So we're going to do x z-score times our standard deviation. So here's how we're going to plug that all in. Remember. So we have the population mean, that is 50. Oh, okay. No, that didn't work. Sorry about that. This is just not my day. Let's try this again. Okay. So let's put our formula. So we're looking for x. So we have our population mean of 50 plus our z-score times our standard deviation of 10, and that is going to give us 50 plus 4 equals 54. So x equals 54, and that would be C. And if this would work, that would be wonderful. Okay, now for our population, again, we are going to plug this all in. Okay, so for a population of 50 with a standard deviation of 10, what is the x value corresponding to z? Oh, we already did that. See, this is where the brain doesn't want to work today. Okay, so we're going to decide if this is true or false. So if you have population of 40 and 50 corresponds to a z of 0.2, then the standard deviation is 10 points. So we are going to break this down using our formula for our z-score. Okay, so x is 50, 40 is our population. We have our z-score of 2. Over our standard deviation of 10. So we are going to change this to do 10 over 2 equals 5. So our standard deviation is 5. It is not 10 points. So this is false. Now let's look at number 2. If our standard deviation of 20, a score above the mean by 10 points, we will have a z-score of 1. So, again, we are going to use, erase the ink, we're going to use the x minus population divided, okay? So, we are going to let x minus y, it's supposed to equal 10. So when we have our z-score, we have 10 over 20, and that equals 0.5. So a 10-point difference above the mean is only half the standard deviation, which means the z-score is 0.05, not 1. So this is also false. So now we're going to talk about transforming every raw score, x, into a distribution, into a z-score. So let's go over some key points. Every x value becomes a z-score, regardless of what the original score represents, stress levels, test results, opinions. We can convert that into a z-score. All you need to know is the mean and standard deviation of that data set. The characteristics of the z-score transformation. Same shape, so transforming scores into z-scores doesn't change the overall shape of the distribution. If the data was skewed to the right or left before, it will stay that way. It's just relabeled in terms of z-scores. Mean equals 0. Once everything is expressed in a z-score, the new average is 0. This is like shifting the entire distribution so that 0 is now the center point. Standard deviation equals 1. We scale all the data so that one standard deviation in the new distribution is exactly 1. This way, if someone's z-score is +2, you immediately know that they are 2 standard deviations above the average, no matter what the original units were. After we do a z-score transformation, we call the result a standard distribution. It gives everyone's score a clear, direct meaning. Positive z-scores are above the mean, negative ones are below the mean, and 0 is right in the middle. So, how is this helpful? Let's say you have 2 groups you surveyed on something like community satisfaction. One group used a 1 to 7 scale, the other used a 1 to 10 scale. By converting both sets of responses to z-scores, we can compare them on equal footing. A z-score of +1 in the first group means the same amount of above average satisfaction as a z-score of +1 in the second group, even though their original scores were different. So here we see 2 different distributions, original population of x values on the left. The mean here is 100, with the standard deviation being 10. All scores are centered around this 100, which is the average, and spread out by 10 points per standard deviation. Now we've transformed this population to z-scores. When you apply the z-score formula to each x value, you end up with a new distribution mean that is 0, and the standard deviation is 1. The shape of this distribution remains exactly the same. It's just relabeled in terms of how many standard deviations each score is from the mean. So every original score, like 90, 105, 115, gets mapped into a z-score. So, for example, 110 would be 1 standard deviation above the mean. If you had a score of 85, that is 15 points below the mean of 100, which would equal about 1.5 standard deviations below the mean. So that z-score is negative 1.5. This figure shows how we switch from raw scores on the bottom axis, like 80, 90, 100, 110, 120, to the z-scores. We're still looking at the bell-shaped curve, and the high and low ends remain the same. The difference is that we've replaced the original units, such as test points or survey points, with a standard scale in terms of how many standard deviations each score is away from the mean. So again, that mean is now 0. And if you score exactly 100 on the original scale, your z-score will be 0. Before, each step along the x-axis might have been 10 points on a test or some other measure. Now we mark one step from 0 to +1 or 0 to -1, which would be one standard deviation. That means that 110 becomes z equals +1, 90 becomes z equals -1, and so on. Each of these points is one standard deviation from the mean. So z-scores are super handy when we want to compare scores that come from different sets of data. Since a z-score is measured in terms of standard deviations from the mean, a z-score of +1 always means that a score is exactly one standard deviation above the average, no matter what the original unit was. Scores from different distributions can be converted to z-scores. This means you can have survey results, again from a scale of 1 to 10, and then another scale from 1 to 5. And after we convert both sets of data to z-scores, they can line up and see who's above or below average. We also get that standard comparison. So z-scores, also called standardized scores, provide a direct comparison across two or more data sets. If a participant's z-score in one study is +2, but in another study it's +1, we know they're more above the average in the first study, even if the original scales aren't the same. So here's some well-known examples of standardized distribution. We have SAT scores. The SATs are designed so that the average is 500 with a standard deviation of 100. That means if someone scored a 600, they are one standard deviation above the average, or they have a z-score of +1, because 600 is 100 points above 500. When we talk about IQ scores, IQ tests, like a Windsor scale, they typically set their mean at 100 and their standard deviation at 15 points. So if a person's IQ is 115, that means that they are one standard deviation above 100, so their z-score would be +1. So they get these distributions by converting raw scores into z-scores. Then those z-scores are scaled to whatever average and spread the test designers want. So again, for the SATs, they chose a 500 mean and 100 standard deviation. And for IQ, they picked 100 mean and a 15 standard deviation. So we're looking at 3 different ways of labeling the same distribution data. So first and foremost, we have the original scores. Okay, we have a mean of 57, a standard deviation of 14. So this is on that top axis. You will see the original raw scores ranging from about 29 to 85. These scores have an average mean of 57 and a standard deviation of 14. So if you have a score of 71, you are 1 standard deviation above 57. Okay? Because 57 plus 14 equals 71. So then we look at z-scores. Then we are looking at z-scores. Okay? In the middle axis, we convert that to 0, and we have a standard deviation of 1. So that means that 57 now is 1, the mean, and 43 becomes negative 1. So that's 1 standard deviation below the mean, and 71 becomes 1 standard deviation above the mean. Notice that the distribution remains exactly the same, although we've changed the labels on the axis. Now, we're looking at standard scores. Okay, finally, the bottom axis, we convert the z-scores into the new set of scores with a mean of 50 and a standard deviation of 10. Now, you originally had a raw score of 57. That z-score was 0. You'd end up with 50 in the new scale. The score of 71, that was the z-score of plus 1, becomes 60, because that is 10 points above the average. And 43, which was the negative 1 z-score, becomes 40 because it is 10 points below 50. Now we're going to do the learning check 3. If we have a score of 59 from a distribution where the mean is 63 and the standard deviation is 8, when we transform the entire distribution so that the mean is 50 and the new standard deviation is 10, what does the old score of 59 become in the new distribution? So we're going to work through this together, okay? So first we need to calculate the z-score in the original distribution. So we have z equals x, the population. So we have 59 minus 60 over 8, which would equal negative 4 over 8, which would equal negative 0.5. So this tells us that the score of 59 was half the standard deviation below the original mean. So half the standard deviation. So use the z-score to find the new score. Okay, so here is that formula. Okay, so here's how we write that out. 50, because we want that distribution right here, it's the new one, plus, then we're going to use that negative 0.0 from here, times 10, because that's new, which would be 50 minus 5 equals 45. Okay, so The new distribution, our original score was 59, okay? It has now become 45. So that is the correct answer. The process converting to a z-score, using the z-score to get a new value, lets us shift from one scale to another while keeping each score relative position on the distribution. So looking ahead, turning our attention to inferential statistics, these are methods that let us use information from a small group, the sample, to draw conclusions about a larger group, the population. So here's how it connects to what we've learned about z-scores. What are inferential statistics? They are all about answering questions like, is the sample result we found actually meaningful, or could it be due to chance? For example, if we measure a small group's average stress level, we want to see if that this group's results are likely to represent the whole population, or if it's unusually different. When we interpret our findings, we ask if the sample population, the outcomes, are noticeably different from what we'd expect from the population. One tool for defining noticeably different is the z-score. If the sample mean z-score is large, positive or negative, it means that the sample mean may be far from the population mean in a practical way. We've seen how z-scores locate an individual score relative to the population mean. This idea can also apply to sample averages. So if a sample average is more than 2 or 3 standard deviations away from an expected population mean, that's a strong signal something's going on. This forms the foundation of hypothesis testing, where we decide if a difference is likely due to random variation or if it indicates a real difference in the population. So here we look at the sample research design. So first we have the original population without treatment. This is the larger population that has not received any intervention or special program. This could be a community, a set of students, or group of clients in a certain demographic. Then, of course, we have our sample. And this is from that larger population. We measure and observe them in the same way. The idea is that the sample will represent the population, so the findings we get from this group can hopefully be generalized back to this larger group. Next, we have our treatment. Okay, so we introduce something new, a treatment, an intervention, like new study skills. The sample undergoes that treatment, and we keep track of how it affects them. And then afterwards, we measure the group again. We look for changes and improvements that might have occurred because of the treatment. So we compare the before and after, or comparing a group without the treatment to the treatment group. So this figure shows a normal bell-shaped curve representing the weights of a population of adult rats. I know, super fun, right? So we have the mean weight of 400 grams. So that is the average weight of an adult rat. Most rats cluster around that center point. The standard deviation to the right might be 420 grams, or to the left 380. So we would have a +1 or a -1. Rats whose weights go beyond that +2 or -2 standard deviation, for example, heavier than 440 grams or lighter than 360 grams are considered to be extreme or outliers on this distribution. Or they're just considered cute little chubby rats. Just saying. So, if that rat's weight is near the z-score of 0, it's right around the population typical. When a rat's weight is near the plus or minus z-score, it's far from the average, indicating an unusually heavy or light rat. But when we look at this, researchers can quickly identify which rats are within that normal weight range or which ones might need special attention. So let's do another learning check together. Andy took 2 exams, one in chemistry, one in Spanish. Okay? For chemistry, the mean, the mean is 30. The standard deviation is 5. Andy's score is 45. For Spanish, did I spell that wrong? Nope, spelled it right. Okay, the mean is 60. That standard deviation is 6. And Andy's score is 65. Which class should Andy expect to have a better grade in? So we can compare how far above the mean Andy's score is in each subject by using the z-scores. So let's do chemistry first. So we're going to do that z-score calculation, and we are just going to plug everything in. I swear, I need to get better at writing that one. Okay, so that would be 45 minus 30 over 5. That would be 15 over 5, and that would equal 3. Andy's chem score is 3 standard deviations above the mean. So this is a really high achievement. Okay, so let's do, leave Andy's score right here. Okay, let's do Spanish now. Sorry, I don't want to erase everything on here. Okay. I'm sorry, I sing when I'm trying to do stuff, or hum, or call it. Hopefully you find some enjoyment in that. Okay, now let's do Spanish. Again, we're just using that same formula. So that would be 65 minus 60 over 6, which would equal 5 over 6, which would equal 0.83. So this is 1 standard deviation. It's less. It is less than 1 standard deviation. Okay. So for chem, we have a z-score of 3. And then for Spanish, we have a z-score of 0.83. So because Andy's chemistry z-score is 3, it's higher than the Spanish z-score of 0.83. He did better relative to his classmates in chemistry. Therefore, the likely answer here would be chemistry, option A. This is a great example of how z-scores can help compare performance that comes from totally different scores. Now, let's go true or false. Transforming an entire distribution of scores into z-scores will not change the shape of the distribution. We talked about this over and over again. We looked at multiple different bell shapes. Come on, come on. We know this. We know this. It is true. When we convert those raw z-scores, we're shifting the scale. We are not altering the overall pattern. Okay, so remember that. Now, true or false? If a sample of 10 scores is transformed into z-scores, there will be 5 positive z-scores and 5 negative z-scores. This is false. Converting to z-scores means that the average will be 0. But there's no rule requiring the number of positive and negative scores to be equal. It's possible, for example, that 8 of them could end up above and only 2 below. So if we have a population of 10, we are not making them equal. That's not how this works. It's not saying that 5 are going to be above and 5 are going to be below. What's guaranteed in this distribution is that that mean is 0. Not that the z-scores are going to be split equally. All right, everyone. I hope this was helpful. If you have any questions or concerns, please feel free to email me or set up a time to have a video or phone chat. I work around your hours, so please let me know if there's anything I can do, and I hope you have a good morning, afternoon, evening, or good night.